once you've mastered linear approximations, quadratic approximations are exactly the same thing with a little more calculation. A quadratic approximation is just that. We're going to look at a second order polynomial and use that to estimate a function that we're interested in. Now the formula we're going to use, notice that this part here, so we're estimating f of x, and we know that f of x is approximately equal to, well, the function at point A plus the slope of the function at point A, that's measured using calculus, multiplied by the change in x, which is x minus a. Since you've done your homework, you'll recognize right away that this part right here, this is our linear approximation. So you did the homework, you did the practice problems. That part of the equation should look very familiar to you. Where does the quadratic come in? Here's the quadratic part. This is the second order polynomial. We're going to use the second derivative to get a more accurate result. And I should be maybe a little bit more specific. This is the second derivative right here at point A. So that's our second derivative. This term is part of the approximation formula. Notice that we're now going to square the change in x, and then we're going to multiply the whole thing by 1/2. Here's our first example. So we have a function which is the cube root of x right here. Now in part A, we are asked to evaluate the quadratic approximation when x is about 1, and then compare our expression to the linear approximation. So we haven't been given a value for x. That we are given in 1.03, but that's for part B. So in A, we're just going to do the quadratic approximation about x is equal to 1, or A is equal to 1. So f of x here is equal to, well, so f of x is approximately equal to the, well, I can write this as x to the 1/3, so 1 to the power of 1/3 plus, I need my derivative, so f prime 1 is approximately equal to 1/3 x negative 2/3, which is going to be equal to 1/3 times 1 negative 2/3, which is equal to 1/3. So we're going to have 1/3 here, multiplied by x minus 1, because we've got a is equal to 1. That's this part right here. Now for the second term, and the quadratic component of our approximation, so we need to have the second derivative. So f double prime of x is equal to 1/3 times negative 2/3 times x to the negative 5/3. And if we evaluate that when x is equal to 1, we're going to get negative 2/9 times 1, which is negative 2/9. So we have 1/2 times negative 2/9 x minus 1 squared. Keeping in mind, with this second term, I'm just following the formula that I showed you on the previous page. Now we can simplify this a little bit, so we've got, not good looking approximations. We've got 1 plus 1/3 x minus 1. Oops. And I could make this a negative 2 over 18, or 1 over 9, times x minus 1 squared. Now to finish off question part A, we're asked to compare the expression we derived to the linear approximation. And so if we had a linear approximation, we'd have 1 plus 1/3 x minus 1, and with the quadratic we have essentially the linear expression plus, well, in our case it was a minus, this example it's a minus 1 over 9 x minus 1 squared. Now let's put in some numbers and see what this looks like. So for B, we're going to evaluate our approximation when x is equal to 1.03. And just as a reminder, remember that A was equal to 1. That's why we had all these minus 1s in our answer to part A. So we can go ahead and do that. So if I want to know the approximation of f evaluated at 1.03, this is approximately equal to 1 plus 1/3 times 1.03 minus 1 minus 1 over 9 1.03 minus 1.00 squared. 1 plus 0.01 minus, I have a really small number here, 0.0001. So that is what I get for my estimation. I hope you got the same. Now we're also, now if we just had a linear, so if I go to part I, if this was a linear approximation, f of 1.03 would be approximately equal to 1.01. Now let's look at the actual value. So f of 1.03 is actually equal to, and this time I've got an equal sign. It's a little hard to tell. My hand control is not what it used to be. These are approximations. The actual value, this is part 2, is equal to 1.03 to the power of 1 over 3, and my calculator tells me that this is equal to 1.009902. So taking a look at what we've done, which approximation is closest? Take a minute to look, and after you look, you should see that the quadratic is closer than the linear approximation. Which makes sense. That's the whole idea. We've added a new term. We've added more calculation in order to get a more accurate result. Now I'd like to give you a little bit of intuition. So suppose that we've got this function that we just looked at, and we were going to try to evaluate it when x is equal to 1. Say that this is equal to 1 right there. If we do a linear approximation, we've got a linear approximation. And let's think of what we were trying to estimate was 1.03, and let's put it way out over here. So here is our approximation. Here is our actual. Oh, and let me make sure that this is linear. So I've written linear approximation twice. That's our linear approximation. This point right here. And where would the quadratic approximation go? What would it look like? Well, quadratic approximations are curved, right? Because the second derivative is involved and it's changing the approximation. So if I wanted to draw a quadratic, it would be between the linear approximation and the actual. And so we might think of this dotted line here. These are the quadratic approximations. So the quadratic approximation is going to be between the linear approximation and the actual. That's like the example we just looked at, where we found the quadratic approximation was more accurate. It's closer to the actual.